So in this video, we're going to go through enthalpy diagrams. Remember that enthalpy is your H variable, and so delta H would be the change in enthalpy from reactants to products as the reaction proceeds. So an enthalpy diagram is going to show the level of energy that the reactants contain, the level of energy that the products contain, and then the difference between them, which is the change in enthalpy of the reaction. So this is a graphical representation of the change in energy between reactants and products. And this can either be shown with or without activation energy. Now, activation energy is the amount of energy required to get the reaction started. And all reactions, whether they be endo or exothermic, will have some amount of activation energy. It's just typically that reactions that are exothermic require a smaller amount of activation energy, and usually the collisions of those reacting particles generates that energy on their own, and then the reaction proceeds. With an endothermic reaction, it's usually extra heat energy that has to be added to get the reaction to occur. And then I leave you this little note here that if a catalyst is indicated or asked about, you have to include activation energy, because remember that catalyst, think biology, is a method of speeding up a reaction like an enzyme. And a catalyst provides an alternative pathway that lowers activation energy. So for me to show the reaction of a catalyst, I have to have something to reference that. And I'll show you an example of that as we go. So things that you need to make sure that you do when you're drawing an enthalpy diagram. You need to label the reactants and products. If a particular chemical equation is given, then you would label it using the chemical formulas for the reactants and products. If it's just in general, you could just write reactants and products. It depends on the particular question. You should also label and give the value of delta H. If a particular numerical value is given, then you would give that back with its specific sign, whether it's positive for endothermic or negative for exothermic. Okay? So let's look at some things for endothermic. So first of all, an endothermic reaction has a positive delta H value. If we see this in a chemical equation, energy is on the reactant side. And when we look at it, the products are at a higher energy level than the reactants. And that's because we have to take the reactants, we have to add energy. And so, of course, that's going to boost the products up to a higher level. So in general, we would see the following. So let's talk about this first one. So this is simply looking at the reactants and the products with the delta H value. So my reactants are at a lower energy level. We have to add energy because energy is a reactant. My products are at a higher energy level. So I have taken the reactants, I've added energy, I've boosted them up to become products. This reaction or this enthalpy diagram does not show activation energy. So here I have the same type of diagram, except for this time I've shown activation energy. So let's go over the subtle ways that they are different. So I have my reactants, I have my products. My reactants are low, my products are high, and the delta H is the difference between the reactants and the products. Notice that I've looked at the delta H here, where my products are and my reactants are, and I even drew a little dashed line to make sure that I measured that out correctly. And I haven't measured it here because this is my activation energy. What this tells me is that my reactants have to be boosted up in energy to this point, right? The peak of this hump in order for my reaction to start. And once it starts, then we go to become products. But the difference in energy between the reactants and products is not the same as this energy hump. It's just this part. Okay? This EA is the activation energy. So let's kind of talk about what this catalyst piece that I mentioned above was. So what a catalyst does is it lowers the activation energy. My reactants and my products do not change when I add a catalyst. The only thing that changes is this hump. So if I were to show the effect of a catalyst here, what I would be doing was making it a smaller hump. So here, notice that what has changed is the activation energy. The activation energy hump is smaller, but my reactants and my products have not changed. My reactants and my products have stayed in the exact same place. So you can be asked to draw an enthalpy diagram and it not mention anything about activation energy or catalyst, and that's fine. And if you did that, this would be what would be most appropriate and easy. If you were asked about a catalyst, you're going to have to show activation energy. Unless you're given a specific numerical value, you just draw a hump, right? And then to show a catalyst, you draw a smaller hump, starting and ending in the exact same spot, but you have to show the decrease in activation energy. Okay, so these would be both two good examples of endothermic enthalpy diagrams. So let's look at now an exothermic enthalpy diagram. All right, so my exothermic enthalpy diagrams. My delta H is negative to show me that the energy is a product, it's being released. My products are at a lower energy position than my reactants. So my reactants are high, we're going to release energy. My products are low. My delta H is negative. Okay. Now notice this one where I'm showing the activation energy. My delta H is still just the difference between my reactants and my products. And notice that in this exothermic reaction, my energy hump, right, just goes from the level of my reactants up to where this starts. It's not this whole thing because my reactants aren't starting at the bottom, they're starting here. So an exothermic reaction will still require activation energy. It's just a lot less. And if I were to catalyze this reaction, right, I would just have a smaller hump. My reactants and my products would still start and end in the same position, but I would just reduce the activation energy. Okay. All right, so let's do two examples. And these are really easy. Like, don't stress over these. All right, so let's look at my first example. 2S plus 3O2 yields 2SO3 plus 791.4 kilojoules. All right, so really the only question that you've got to ask yourself is, where is my energy? Is it a reactant or a product? And what does that tell me, right? So here, my energy is on the product side. So what do I know if it's on the product side? It's exothermic, right? So that means when I'm drawing this out, I need to have my reactants high, my products low, and my delta H needs to be negative. That's it. So let's draw that. So I'm going to draw just an axis. I'm going to have my reactants high, arrow down, my products low, and then I'm going to write in what my reactants are. 2S plus 3O2. Here's my products, 2SO3. And then I need to label my delta H, negative 791.4 kilojoules. And that is an enthalpy diagram. This particular one didn't ask me anything about activation energy or catalyst, so this is perfectly fine. If I wanted to draw it with my activation energy hump, I could totally do that, and it would still be fine. So I'd have, here's my reactants, little hump, products, 2S plus 3O2, 2SO3, and I'm going to label it on the inside because I'm running out of room, 791.4 kilojoules. I would just make sure that I show that this is the 791, not this hump, okay? Because it is just the difference between the reactants and products. Here, because I don't have the hump, it's obvious because it's this arrow. But here, because of the hump, you need to make sure that you're explicit, that it's the difference between reactants and products. Both perfectly correct. All right, so let's do the same for our last one down here. Br2 plus H2 plus 78.80 kilojoules equals 2 HBr. So this time, my heat term is on my reactant side, so I know that means that this is an endothermic reaction. And so I need to draw it with my reactants low, arrow up, my products high, because I'm boosting them to a higher energy state. Br2 plus H2 yields 2 HBr, and the difference is a positive. Make sure you have that plus sign. Be explicit, 78.80 kilojoules. If I wanted to do this and show activation energy, again, reactants, big big hump, products, Br2 plus H2, 2HBr. Make sure that you're explicit that it's the difference between the reactants and the products and not the whole hump that we're talking about, 78.80 kilojoules. And that's it. That's really all there is to enthalpy diagrams. Okay? You just need to know how to take an equation, interpret where your energy is, and draw it appropriately.